minutes. Let's start. So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. And my name is Francesco Petruccione. I'm at the moment the interim director of NITheCS. Yeah. So thank you very much for joining us this afternoon. After a week that was a little bit chaotic for most of us, I guess, and I hope that you're all okay. So this afternoon we are performing an online experiment because we've never done it before within the context of a NITheCS colloquium. We organized a panel discussion that was suggested by Professor Barry Green, that you see amongst the panelists. And as you know, Barry is the director of AIMS in Cape Town, in Muizenberg. Yeah? And with us is also Professor Bernardo Rodrigues, who was at UKZN, was a colleague of mine at UKZN, but is now at the University of Pretoria. But physically, he's sitting in Cape Town at the moment. Yeah? And with us, the third panelist for this evening is Professor Bruce Bassett, and he's also affiliated with AIMS and UCT. Yeah? And unfortunately, our fourth panelist, Professor Wolfgang Decker, is not able to be with us this afternoon because of little health issues that popped up at the last minute. Yeah? And you see amongst the panelists also Professor Sinaisky, who, as most of you know, is our standard backup plan, because we are using the Zoom license of UKZN, and he kindly acts as co-host in case my connection dies for whatever reason. Yeah. So without much further ado, I think I will ask Professor Rodrigues to start, yeah, and he will introduce us to the topic of computation as a tool for solving theoretical problems, yeah, and the title is of course perfect for an institute like NITheCS, yeah. So Bernardo, if you would like to start, you are most and welcome. The floor is yours. Sorry, sorry, Bernardo. I forgot to ask the participant as usual if they have questions. Please, there are not so many of us, so please raise your hand, and we will make an arrangement to allow you to ask your question directly and get involved in the discussion. Yeah. So Bernardo, sorry, over to you.
Thank you, Francesco, and thank you all of us for this opportunity, which is, I think, unique in its own right. And the title of this discussion is very well suited for a sort of considerations, but I would like to refine my contribution basically on some theoretical problems that have stemmed from algebra and have become amenable to being solved from a computational perspective. One of the things that for many years has been celebrated was the classification of finite simple groups in algebra. And it was very instrumental at some point, the usage of computational techniques to determine the character tables associated to such finite simple groups, particularly those of very large size. Other problems that I have come about and have become sort of familiar to me have been problems posed in geometry, particularly in affine geometry and projective geometry, in classification of finite planes. The classification of a finite plane of order 10 has been open for many years, and it was sorted by Clement Lamb via a computational solution. And other topical problems that I have encountered myself were in affine geometry, in classification of what they call the art blockage geometries related to affine geometry of three-dimensional field of 4 elements. And in here, my contribution has been with a colleague at Michigan Technological University, Vladimir Tonchev, and we sort of sorted the problem, which was initially posed theoretically through a means of experimental computation. So I'll leave it to this, and I think Bruce may come in so that we then liven the discussion. And if there is anything that I should further add, please feel free to ask.
Thank you, Bernardo.
Yeah, thanks so much for the invitation. The question is, how has computation impacted theory? And I guess the question that comes up for me is, what do we mean by theory in this context? You could say a theory is the sort of thing that you don't need a computer for, but then you end up in an oxymoron. What do you need a computer to do non-computer work? So perhaps instead of theory, we could say, how has computation affected fundamental science? But then, of course, the question becomes, well, what is fundamental? What is fundamental science? So in a sense, I'm kind of asking myself, what do we mean? And maybe that's the point. Maybe the point is that there's this fundamental shift in what we mean when we say science, theoretical foundational science, because I think at least so I should talk very much from astronomy, from cosmology, and more recently from artificial intelligence research. The idea of purely theoretical science has disappeared more and more. And recently I saw on Twitter, someone asked, there was a bit of a backlash against machine learning. And they said, there's all this hype about machine learning. What has machine learning done that we couldn't do before? And I thought that's perhaps the wrong question, because if one has a really fundamental theory of a topic, then one shouldn't be doing machine learning. One should be doing a rigorous statistical analysis based on that model. Machine learning is exactly useful when you don't have a fundamental model or when you don't know how to calculate. And it provides a kind of a bridge to being able to do something with that problem. At least that's my current view. So some examples, so this is not theory, but so this is more, going to the question, where's machine learning actually useful? And there's a couple of examples. One, where, for example, we have a theory, but it would take 100 hours of supercomputer time to get the answer. And now we want to compare this model, which maybe has 50 parameters, to data that we have in the real world. So how do I find which parameters are correct ones to best describe the data of the real world, such as large n-body simulations? I see Shazrin, if you're running big computational models and it takes 100 hours on a supercomputer to run one model, how are you going to fit those models, which you might need to try 100,000 models? How are you possibly going to fit that model to the data? Well, machine learning can help by approximating the output of those 100-hour simulations. Maybe it only takes you 5 minutes to get a pretty good approximation to what the 100-hour simulation will take. So suddenly you can predict the solution within some accuracy using machine learning. So if you had infinite computing power, you wouldn't use machine learning in that context. You would do the proper calculation. And I imagine that there's many examples like that. The other example where I think computation is extremely useful is if you just have a huge amount of data and you, in principle, could do it properly, but you just don't have enough time and computing resources. Yeah, maybe that's a good place to start. I mean, the questions I'd maybe pose to the audience and to my other panelists would be questions like, what is computation doing to the nature of the way we do science, the culture of how we do science? Like, are our standards of rigor dropping, or will they drop? For example, when I was a graduate student, I wrote all my own codes from scratch. That had some advantages because it forced me to understand what I was doing. The disadvantage, of course, is that my code was only checked by me. And so there were probably many bugs. Now, of course, there are many packages, TensorFlow, NumPy, that often people use as a black box. And so, I think there's an interesting question of what is happening to the definition of science, to the nature of fundamental research. And then I think maybe this question about, we've been talking about computation, and I guess there's a question of, where do you draw the boundary of what constitutes computation? But I think a very interesting question is, will AI be able to do fundamental research on its own? Instead of just being a tool to help answer questions, will it be able to come up with ideas? And I have my own views on that, but I would be super interested to hear from the audience and from the other panelists. So maybe I'll stop there.
Thank you very much, Bruce. And I think if I can add my 2 bits and pieces, I think there's also another aspect to the computation that maybe was implicit in what Bernardo was saying. And that is, for instance, there are also programming languages like Haskell or Lisp, that formalize kind of systems of mathematical logic. For instance, both Lisp and Haskell are functional programming languages, so that they're essentially the realization of lambda calculus for computers. And those are also tools that can in principle be used to prove logic statements. So that they're also tools to achieve to some theoretical results of sorts. So there is not only the number crunching aspect of computational. There is also the possibility of implementing mathematical logic in code, and let it do whatever needs to be done. For instance, just a stupid example. Yesterday evening, I had a very nice chat with my PhD supervisor, who is now, of course, retired. And his hobby is now to algorithmic music. So he composes music with Haskell. So that's really something really, absolutely new to me, and I have no ambitions to copy him. Because I'm not very musical. But that's really fascinating stuff. And you can do things that would require probably much more time and effort otherwise. So there are those 2 aspects. There is the number crunching and the more, let's say, logic algebraic approach to computation, where that we can use as a tool to reach something.
Okay. I think there was an open question by Bruce that one could try to sort of drop in a few ideas. And one of them is, about the shift that computations as tools have or are bringing into the whole defining pattern of science. My view of it is that I don't particularly think that the helping hand of computational tools will shift the fundamentals of science per se. The way I perceive it is that one should use a doses of computation to help one guide one's sense and understanding of what can be done computationally and what cannot be done computationally. In many occasions, I have encountered situations where certain journals, for example, had drawn the line on how much of computational work they would be willing to accept. But other journals which are also leading, for example, the Journal of Symbolic Computations, for example, which is very well respected, has then that flavor that Francesco brought in, where to a very large extent, they are probing calculational and logic understanding of the whole paradigm of calculations, let alone the number crunching part of it, but the theoretical and the model-like and logic-like perspective of it. And many leading journals have also established one section of the journal for computational publication. So what I'm trying to say is that one will not lose the science. One will enhance the science by bringing the computational aspects, but then answering the question still from a theoretical point of view or perspective. Yeah.
Yeah, no, thank you very much, Bernardo, for that. And speaking of machine learning, there was recently, or there have been recently several papers on machine learning algorithm rediscovering laws of physics. Yeah, and to test the approach, you try to rediscover Newton's law by feeding the machine learning program data on the movement of planets and so on and so forth. Yeah. And it seems to work, yeah. So that maybe by feeding machine learning algorithms with much more important data sets, yeah, like the ones that probably Bruce operates with on a regular basis, maybe some other evidence might emerge. Yeah? And I see that Barry is back with us, because I think we lost him for a few minutes. Maybe we should give him the opportunity to comment as well. Are you with us again, Barry?
Yes, I am. Thank you, Francesco.
Here we go.
So let me just find my bearings, and let me just so everybody has introduced themselves, and Bernardo has said a few words. Has Bruce said a few words already?
Yes. We all said a few words, and
okay.
We just want to give you the opportunity to give us your point of view, and then we can open a general discussion and see how it goes.
Sure. So it's a great pleasure to be part of this panel discussion, of course, and and to acknowledge that of my own experience has been that of a pure mathematician, number theory and algebra, but always interested in computation and where it can play a role in helping to solve problems, and of course some problems not from pure mathematics, other areas as well. So there are a number of striking examples, and if one, and I know Bernardo and would have mentioned some of these related to group theory, like the classification of finite simple groups, or the four-color map problem, where computation played an enormous role. And then of course there's the Kepler conjecture, which was the sphere packing problem, which was a 400-year-old problem, and finally, in 1998, Thomas Hales from Michigan solved this using a lot of computation. And at the time, I was at the Arbeitstagung at the Max Planck Institute in Bonn, and he was one of the speakers. And so he spoke about a little bit about his proof. And then one of the other great mathematicians of the century, Yuri Manin, got up and he said, well, what is a proof? Because this had appeared in the annals of mathematics, but it needed a computer to check it. It needed a computer to be, in fact, the referee. Okay. On the other hand, quite often in mathematics, you scan down a proof, and this happens in theoretical physics as well. And you say, oh, well, this part is fine. I have to check that part very carefully. And so the referees, they check the part that they feel is new and that they don't understand completely, which will close the gap and make the proof. Now, of course, all this was done by a computer. And in fact, in the annals, it actually even mentions that this was a computer-generated type proof, but it solved the problem. In fact, the problem was how to pack spheres in the most optimal way in a box. And actually, these are the things that grocery people know. If you pack oranges, well, you put a row of oranges down the bottom and across, and then the next ones you put in the gaps. Okay. Well, it took over 100 years before Gauss actually proved that if it did it like this and they all belong to a lattice, then this was optimal. And it took another 200 years before Hales proved this generally, because you can think of all kinds of piles that you could make. So that was a wonderful example of computation solving a really theoretical problem. And of course, it was just an illustration of the power of computation. Now, Wolfram Decker would have said a lot more, because he's a computational scientist, having developed singular with a number of other people. But there was one experience I had in my own career, and I'll just share that with you. So perhaps, Francesca, if you could go to the first page, and then I'll do the first and the third.
Do you want me to share it for you?
Could you share it?
Yeah, okay. I just need to open it before I, first I need to remember where I saved it.
No problem. That's the advantage of a physicist and not a mathematician. Sorry.
Yeah, okay, I found it. Now I need to share it for you. Here we go. Okay, this is the first page.
Okay, if you look at that's fine. If we look at the first page, you see we've got on the left-hand side, we've got an elliptic curve defined over the rational numbers. And on the right-hand side, we reduce modulo prime. And then we see, well, for some primes, p equal to 2, 3, and 5, some of the coefficients go to 0, modulo 2, or modulo 3, or modulo 5. And we get what we call a node, or we get a singularity. Okay, now the question is the inverse. So let's go back, let's jump to page 3. The next, that's one, yes. Okay, so now we get a curve and it's defined over a field of characteristic P, and we're asking, and it's a smooth curve, and we want to lift it up to something over the rationals, or over a field containing the rationals, and so that it's a smooth curve. But we also want a group to work on the curve to move the points around, and the same group must work on the left-hand side. Now, this is quite a deep problem. It was conjectured to be possible for cyclic groups by Jean-Pierre Serre, and I worked on this with a colleague of mine, Michel Matignon. We were able to do it for P and P squared cyclic groups. But in fact, what it does mean is, for most points, there's no problem. And there are certain points you'll see, y4, y3, y2, and y1, where the problems may happen. And you want to lift it in a way that you can make a nice smooth surface at the top. So you want to close it with a disk. Now, when you close it with a disk and you're having a group acting on it, the disk is actually like a formal power series ring. So you're working with power series. And when the group acts on the power series, it's an iteration. Now, if you're going to iterate power series, so the variable becomes the new power series, and you do this a few times, very soon you are having an enormous amount of computation you got to do. And so what I did with Michel Matignon is we worked on this, and we looked we had to discover where the fixed points were. And in fact, by doing this for small primes less than 11, less than or equal to 11, we were able to see that actually the fixed points are always equidistant from each other. And so this then led to some further work. And finally, we proved some interesting cases which appeared in the American Journal of Math. And then finally, a colleague of mine from Penn, Florian Popp, solved the whole conjecture using logic model theory as well as arithmetic. And that appeared in the Annals in 2014. But for us, the problem was that we had to understand how to work with this and to discover theoretical tools, but we needed evidence. And the evidence came from actually being able to do computations with power series in the very simple cases. So this is not symbolic computation as you would have if you were doing Grosvenor bases or you're working with singular. This was simply computation with Mathematica or Maple, but which enabled us to actually verify certain small cases. And, you know, mathematics is amazing. The amazing thing is sometimes the very simplest looking thing turns out to be the general behavior. But now go and prove it. And that's where the computation helped us. So this was just a story that I had myself. We were fortunate enough to do this in Oberwolfach. And then many years later, the problem was solved. So I believe that mathematician must be able to combine both the theoretical and the computational side, and to benefit, not be necessarily an expert in both, but be able to benefit from both facilities, I would say. And so that's the story I wanted to tell this afternoon. Thank you.
Yeah, thank you, Barry. Then I can probably stop sharing the screen. Thank you very much for sharing this very, very interesting and successful story. I don't see yet any raised hand or questions from our audience. So please, if you have comments or other success stories of computation and theory that you would like to share, please just raise your hand and we can allow you to intervene and make your point. Here we go. The first, Zurab, please, welcome. You're welcome to ask your question or make your comment.
Hello, thank you very much. Hello, colleagues. Since you invited to share, I can also share a small story from last year. Would it be possible for me to share the screen?
Yes. Do you have the right to do so, or do we need to give it to you?
I don't think I have at the moment.
Okay. Then here we go. Now it should work. Now you should have a green share screen button.
So now I have rejoined and I will be able to share.
Yes. I made you a panelist now. Yeah. So you can share whatever you want to share. Yeah.
I found the button and now I will do this. Okay, great. I think I found it. So I work in the field of category theory. And so this was something quite unexpected last year. That happened. So we study in categorical algebra, we study properties of categories. And for those who don't know what a category is, you can think of it as a very, very wild generalization of a group. We were interested in properties of categories that can be encoded by integer matrices. And it seemed to be impossible to determine an algorithm that would decide when one property implies the other. So when a property given by one matrix would imply a property given by another matrix. To check it by hand is almost impossible because categories are very general structures and you don't even know which representative examples to look at. And then unexpectedly, our colleague, my former student, Dr. Michael Hofnagel, he found an algorithm. And so he invited myself and my colleague in Belgium to work on this together. And we refined the algorithm a bit further, and it became clear that the algorithm is such that it can be implemented on the computer. So we did that. And for the first time ever, we were able to display these huge pictures of relationships between matrices, these implication relationships I talked about. So this is just a sample fragment of a partially ordered set, which is actually infinite. So computer can only display for us finite portions of it. In here we have matrices of certain fixed dimension, and the colored matrices that you see, they are the conditions, properties of categories that have been considered in the literature. And the gray matrices are the ones that have never been considered in the literature. So now we know the interdependence of all these conditions without having to check anything for free from this big table that computer can generate. And it was quite fascinating that we were able to use computer this way. So just to give you a bit of a feeling, to draw this picture by hand would probably take, I would say, maybe a year of computation, something like that. So it was a very nice point, and since then I became in love with using computational techniques for theoretical mathematics.
Wonderful. That's a wonderful story. Thank you very much for sharing with us. Does maybe one of our panelists want to comment and reply?
Well, I just want to commend Zurab. I think that's great, and so there are very, very many that are not shaded, and so can you learn from those?
Sorry, what do you mean? If I can learn from those?
Well, you know, you've got the ones that have a little bit highlighted, I guess one should say.
Yes.
And then you've got a huge number which are, I mean, which are not highlighted, but obviously some of them could be very interesting or not.
Exactly. Yes. So each highlighted matrix is basically a concept which has a number of papers for 50 years dedicated to it. I mean, some of them for longer, some of them for shorter. So you can imagine each of these new matrices now one can investigate them and write a whole literature about each individual ones.
Okay.
We were trying to see if there is any kind of any symmetries maybe that this picture has, but it seems to be very wild thing. It's very, very concrete mathematics in the sense that there doesn't seem to be any general principle as to how this poset is organized.
Yeah. And may I ask one more question? You called it a Hasse. What was the name of the diagram?
Hasse diagram?
Hasse diagram.
Yes. So is this a standard concept for this kind of
yes,
thing?
a Hasse diagram is a standard way of displaying a lattice in the sense of algebra, in the sense of lattice theory. So the nodes are displayed, and when one element is less than the other, but there's nothing in between, then they're connected by a line.
Okay. Thank you.
Thank you, Barry. Thanks.
And just out of curiosity, what computer language do you use to solve this problem?
Python. The algorithm is actually not difficult. It's very simple to implement it on the computer, but the amount of computations is what is really big, but computer helps. We used Python, and all three of us did it separately to make sure that our code was doing the right thing. So we had the same result after some refining. We had the same result. All three of us, we were happy, but we all did it in Python.
Perfect. Thank you very much, Zurab. That was really very.
Thank you.
And in the meantime, we have another participant, Bruce Watson, who would like to comment or ask a question. So Bruce, please, the floor is yours.
Thanks very much, colleagues. I must say I'm really enjoying the session today and the discussion. As someone who actually worked on Maple a long time ago, I've got a very good appreciation for the good work that's being done using these symbolic tools. I also very much agree with your comments, Francesco, about the cleanliness of the language and the possibilities of actually embedding proofs within the language, like Haskell and ML and the various proof systems like Coq that are based on type lambda calculus. So with that, I should also mention that I come from a background that is related to the correctness of algorithms. And so I'd like to make a provocative statement and just see if it, if there's some comment from the panelists. And that is a lot of the use of computational sciences to do fundamental science, whether it's physics or pure mathematics and so on. In a sense, the results, like the 4-color result, could arguably be called conditional proofs, because they rest on the conjecture of the correctness of the algorithm. And very often the correctness of the algorithm is what's left out. I think most of us are accustomed to debugging something into correctness, but that's not the same as a correctness proof for the algorithm. So it's, as I said, it's very provocative to say that, but I'm curious to just hear commentary on that. Thanks.
Yeah, no, thank you very much for that comment, Bruce. Thank you. Does anyone of the panelists want to reply?
Thought-provoking challenge.
Yeah.
Maybe I'll just comment to say that it seems eminently correct that there are only partial proofs. And even beyond that, since computers are not actually digital, they are analog emulators of a digital ideal, as I always say. We can never be 100% sure that any specific running of a computer didn't generate an error somewhere. Some cosmic ray didn't do a bit flip. So I think there's a very interesting question about when you really want to believe a proof. Of course, one way you can do it is just rerun it many times, but that in itself is not a proof. So yeah, I think there's some very interesting fundamental issues around the notion of a proof when you're using a computer.
Yeah, thank you, Bruce, for the comment. I see. Yeah, Zura, please. You're still on the panel. You're welcome to.
Thank you. Sorry, may I also comment on that? So I'm not sure that proofs, when they are checked by human beings, are 100% accurate either, especially when mathematics is complex, when it builds on each other, and so on and so forth. So I think that using computer as a third opinion is very good, actually, even for proofs that humans have checked and claimed that they are correct. But of course, it will take some time to implement all these theorems on the machine. So I'm not sure that existence of computers compromises too much the concept of proof, because also for human beings, it's impossible to check very long proofs that rely on, I mean, you basically have many people checking them, and that's how you know it's correct. I mean, otherwise, how do you know? And in the same way, if you have many different algorithms for approaching the same problem, maybe it means that it's fine, no?
Yeah, no, that's I think that's a very valid comment. Yeah, thank you.
Bruce made it very provocative and left it a challenge on the provocative sense, but it just began dawning on me that a comment that was made by Barry on the classification of finite simple groups has opened up, in fact, a lot of questioning about the rigor and the proving of the celebrated theorem, which is called the Classification Theorem. And many people have decided now that they go about in verifying the proof, the so-called celebrated proof. And it has now, what was thought to be an easy thing to do, and maybe something that would not take as much time, it's proven to be a challenge because new theories have developed as a result of trying to verify what was believed to be incomplete. New theories have developed and surfaced. But again, the whole entire purpose of checking has dramatically come to a halt because a whole host of persons who are able to verify that proof are either retired, have passed on, or don't know enough. So, and as Zurab said, now we are having to rely on certain things to be done computationally as well. So, I mean, the helping hand of the human is no longer able to do everything. And not because the humans are unable to, just because of being unable, but simply because that knowledge and that generational gap in knowledge cannot be replenished immediately, because some of these people who knew a lot about finite simple groups are rather old, or they've retired, or simply don't do mathematics anymore. And the new generation is not interested in that problem. And I mean, there is that now where we are, where we cannot complete the proof because we don't have enough ability around us. So that can degenerate into another problem if one is, I mean, one doesn't really know how far one can really push these things. Yeah.
Yeah, no, thank you for that comment. But I see Bruce Watson raise his hand again. So please, Bruce, if you want to reply to the.
Thanks so much. Yeah, in fact, we shouldn't have too many Bruces in one session. Thanks, though. I really, really enjoy the feedback actually from all of the panelists, and very much agree. So I don't mean to undermine in any way the strong work and the strong possibilities. I think it's very interesting to observe that the vast majority of software is, of course, made by people who don't understand correctness and are just trying to put something out as an app or a website or something like that. And very fortunately, in the more fundamental sciences, we typically have people working on the algorithms who are much better equipped for the underlying correctness argument and so on. I worry a little bit sometimes, but I'm not equipped personally to explore this. But you know, the possibility that something lurks under the hood in the implementation of Python or various machine learning libraries, which are developed by third parties. And generally, we would hope that open source encourages, you know, the detection of bugs. There are, of course, ways of mechanically checking the correctness of these algorithms. So that connects back, I think, also with what several of the panelists have said. And hopefully that becomes the next challenge, is how to fully automate these correctness proofs, not only of the underlying mathematics, but the algorithms themselves. Thanks.
You know, thank you, Bruce, for this comment. Are there more questions from the audience? No, I don't see any at the moment. Or other, maybe we can give the audience a minute to think about further questions and comments. But I wanted to make a comment on what Bernardo just said. And going forward, Bernardo, what do we have to do? Yeah, because I mean, it's pretty obvious that the way of doing science is changing very quickly. Yeah, it's all open and a mixture of theory and computation affects theory, and theory affects computation as well. Yeah? What do we need to change in the way we train our students? Yeah, because they will have to live in this world, yeah, where computation and theory are interchangeable, so to say. Do you have a suggestion, Bernardo?
That's a difficult one, because, I mean, I'm just picking up on what Bruce Watson, I'm referring to the surname because I have another Bruce in the audience to make the difference. What Bruce has just said was, we don't have enough expertise in both places, both the theoretical and the computational. And we come from a very classical training way, where you were trained in most of the theoretical undertaking. But again, I also hear what Barry said about the need for us to start bridging and trying to equip ourselves, even though we are not going to become a specialist on both worlds, but we need to have flavors of both worlds to be able to equip ourselves, and at the same time, I think, equip our students. I myself, when I first got trained, was exposed to computational, but to a little extent. And only further in the development, I then began picking up the importance of computational understanding, and sort of self-trained as I went about and began understanding that the things that I had learned in undergraduate in computer science, although basic, they then had a bigger perspective, and I needed to learn more and equip myself, and as I went on. But to answer your question, I think you're correct in saying that there's been a big shift, and we need to start thinking more on equipping dually the students for the competencies of both worlds, of the needs that come as they develop and as they become proficient in the theoretical and also in the computational side. It exposes them to more opportunities in the market of work, and it gives them edge and ability to be participants in many avenues of knowledge, I think.
Yeah, thank you, Bernardo. And I think Barry raised his hand. So Barry, if you would like to comment as well.
Sure, I'd just like to add or to build on from what Bernardo has mentioned, you know, about people getting elderly and then passing on and things being forgotten. So I think we will always be attracted by the challenge of the problem. And so if one goes and looks back at for example, the classification theorem that he referred to of simple groups, the big theorem, Fate-Thompson theorem, was proved, I think, in the 70s. But just in 2005, there's this computational guy, Georges Gontier, who gave a computational proof, saying that every solvable group must be odd, or every odd group rather is solvable.
Yes, it's solvable,
and he did that using theorem proving software. So I think that's the challenge of the problem. Many things will be forgotten, but the challenge of the problem is what sort of attracts people, whether they are specialists in one area or the other. And I think that will remain because because it's actually a human quality about what interests you.
Yeah.
What doesn't interest you will be forgotten, of course. But if it is appear that it's useful somewhere, it'll stimulate interest again. The challenge of the problem will help that. Thank you.
Yeah. No, thank you, Barry, for that. No, so that's still your hand, Barry. No, since we still have roughly 10 minutes, and I don't see urgent questions from the attendees, can I maybe suggest that we start the wrapping up, and we ask each of the panelists to make a final statement, and we can ask also the new panelists that joined us since the beginning to give us their statement as well. Let's start maybe with the two Bruces. Maybe Bruce Bassett, would you like to start?
Sure. Okay.
Yeah.
I think maybe I'll highlight one thing that we didn't get a chance to talk about, which is that, physicists have had this long tradition of theorists and experimentalists kind of competing, but also benefiting from each other. Experimental breakthrough would lead to, theorists having to try to explain this new observation. And then theorists would dream up some crazy idea, and then experimentalists would go off and try and test it. And it's an incredibly valuable and important interplay between the theorists. And I think there's a new element to that, which Barry alluded to, which is of using computation to almost do experiments. One can think of in many ways as a computation like a torchlight. You go into a big room, it's dark. You're trying to explain what is the structure of this room, what kind of furniture is there. You switch on the light, which is doing an experiment. You see something and something moves and you're like, well, what was that? Or you see something weird, and then the theorists go, okay, let me try and explain that. And for example, deep learning in artificial intelligence is a bit like that. It works. We don't understand really why it works so well. We have self-driving cars to some degree, but we don't understand fundamentally why deep learning works. And I think that's an incredibly valuable thing, to use computation as a torchlight to throw light on different aspects of interesting questions, making discoveries, stimulating people to work on the fundamental understanding. So I think that's very, very valuable. So yeah, let me call it quits there.
No, that's a very interesting comment, Bruce, because also from my personal experience and in my research group at UKZN, we work mainly theoretically, but we have also a small experimental operation in quantum optics and things like that. And the only language in common between the experimental quantum optics people and the theoretical people is essentially machine learning. Yeah, so it's really a tool to bind diverse cultures, yeah, in physics. So that's really very interesting. But I see that Bruce Watson already posted a comment in the chat. Maybe Bruce, would you like to share it with everybody in person?
Yeah, thanks. Thanks for giving me a second for that. I appreciate that. My comment was basically a follow-on from what Bernardo said, but I think would be for me a good personal closing to this, even though I'm not a proper panelist. And that is, it seems that there's a need for a proper student trajectory or proper curriculum for the computational sciences. And I think it's very tempting to wrap it in under normal computer science, shall we say. I personally lament maybe a bit of regression that's happened globally, not just for us, but globally in computer science, where the vast majority of people graduating will, of course, build apps and websites and things like that. And those things are tremendously profitable. But I have this nagging feeling that the underlying skill sets for that kind of thing is a little bit different from what would really be needed for computational sciences. So I would like to see some a strengthening of that, you know, bringing it back to what Bruce number 1 or Bruce 0 mentioned, and that was, you know, that digital computers are, of course, not even deterministic. So this is something not understood by most computer scientists. That correctness proofs for algorithms have been understood. There's a calculus for these kinds of things that goes back to the 1960s and early 1970s. But of course, these things are not feasible for anyone other than someone designing a pacemaker or an autopilot or something like that. So I'd like to see some of these lost skills come back and hopefully serve the computational sciences community more effectively than the tempting hack and slash approach that most computer science graduates do. Thanks.
No, thank you very much, Bruce. 1 or 2, depending if you use Python or Julia.
Indeed. I'm a discrete mathematician, so I'll be Bruce 1.
Okay, very good. Yeah, no, you know, that's a very valid point, and that will be, and I think that is a discussion that will also define what NITheCS will be about, yeah, because now we have theoretical and computational in the name, yeah, and we need to find a way to engage and train people in both, yeah. So it will be essentially at the core of the identity of what this new institute needs to do. Yeah, we need first to find out what exactly it means to be a theoretical and computational sciences institute, and how can we attract the new generations with the necessary skill to be part of it. Yeah. And I follow now the order in which you appear in my top panel in Zoom, and Zurab is next.
Thank you very much, Francesco. So I will share my screen again just for a very quick demonstration. So it's we have a second-year module called Foundations of Abstract Mathematics, where in the first term I teach students what is a mathematical proof. And so we follow natural deduction, that's very well known in proof theory. And it's been, I've been running this for a few years now, and at some point, idea emerged that maybe we should have students writing up their proofs as an instance of a computer code. So basically, a proof can be seen as an instance of a computer program. And so we started with a group of students. We are now developing the specific language and proof assisting software, which will be intelligible for the second-year students, because the proof assisting software that exists out there are very complicated at the moment, with huge, many pages of documentation. And so what you see here is already one of the proofs produced through this software, which is transitivity of the subset relation. You see here we have theorem, and the computer knows which axiom it needs for this theorem, and it displays the axiom as well together with the output of the theorem. And if there are any mistakes throughout the process, then errors will also be displayed. Now, these vertical lines, this is something that corresponds to the natural deduction in Ficht's notation. The opening bracket means that assumption begins, and for instance here, the closing bracket here means that I'm talking about the vertical bracket, means that the assumption has been concluded and we can step out of the assumption. So I do think that we need to teach proofs and programming at least once simultaneously, where students get to see how they can use computer program to design a proof, and this way get an understanding of also the structure of the proof much more rigorously. So they have to really detail all the steps. You see, this proof looks very complicated, but it's a proof of some very simple mathematical fact. And so the main challenge for students is to realize that even for things that we seem to be obvious mathematically, when you actually want to prove it in all the steps, it requires a lot of elaboration. And so computers will be useful in that regard to bring that awareness. That's all I wanted to say. Thanks.
Yeah, thank you very much, Surab. That's really fascinating. Yeah, and I think next is Barry. Huh? Yeah.
Well, I would just like to say that I found this most enjoyable, and you know, it's the diversity of what can be achieved scientifically with math and with other things together. Maybe another topic would be the gems of Paul Adosh or something like this. Just because great minds bring great ideas, and whether that's with computation or with theoretical analysis, this is what is stimulating. And so I found this afternoon very stimulating. Thank you, Francesco. And of course, thank you to everybody who joined in. It was a lot of fun. Thank you.
Thank you very much, Barry. And last but not least, Bernardo.
Thank you. Thank you, Francesco. I really enjoyed the session. And I'm staying with a couple of ideas and a couple of things that I have learned from all of you. But one particular one is the reference that Barry made on the sphere packing lattice and the density problem. And this is a problem that has cut so many ways and through so many areas, including error correcting codes. And this is one of the things that John Conway also put his hand into when he tried to prove the largest of the Conway groups and linking that with sphere packing lattice. And John Sloan, him and Sloan were then able to write that monumental book on sphere packing lattice and codes. And about a year and a half ago, I delved into that and put my finger into something that Barry has just said is the idea and the flame that will remain. I then probed the Conway largest group, which is Conway 1, and it acts on a 24-dimensional vector space over the field of two elements. And I was able to prove that that particular group is the automorphism group of an optimal code of, let me tell you the length slowly, 98,280. That's the length of the code. And the dimension is 24. And the minimum distance is 47,104. So you can correct that many, the integer part of that divided by 2. So these large objects, these large groups have found their way of expressing themselves and realizing themselves into communication theory in error correcting code. I mean, we're really putting our finger in things that would not have been able to do if we hadn't helped ourselves with the knowledge of the computational softwares available. And I mean, I just thank you for inviting me to bring whatever I could bring into this conversation. Thank you very much.
Yeah, no, then thank you, Bernardo. And I think now it's my pleasant task to thank you all. Yeah, both the original panelists and the additional panelists that we coerced in the course of this colloquium. So thank you very much to all of you for your contribution. And I think our first experiment of a panel discussion in the NITheCS Colloquium was quite successful. I also enjoyed it. And we raised lots of questions that might require further panel discussions. And at some stage also some implementation, yeah, after the discussions. Yeah? So thank you very much to everyone, to the panelists, and to our faithful participants that are with us every Monday. And I guess I'm not sure whether we have already shared the announcement of next week's program, but if not yet, it will be in your inbox shortly. Yeah. So thank you very much again, everyone, for your contribution, and I hope you enjoyed it as well, as much as we and the panelists enjoyed it. Yeah. So thank you very much. Have a good evening and stay safe. Yeah, and because there is still COVID out there, although we had other problems last week. Yeah, thank you. Have a good evening. Bye-bye. Cheers.
Thanks, Barry. Thanks.
Bye.
Thanks, Francisco.
Cheers. Thank you very
Bye.
much. It was
Bye.
lovely.
Thank you.
Bye.
Bye.
Thank you very
Bye
much.
then.
Goodbye.
everyone. Bye.
Thank you. Bye-bye.